So this problem was in our notes. So we wanted to find the flux of this three-step problem because you have a top, you have a sides, and you have a bottom on this thing. So the other ones were really pretty straightforward because we only had one particular surface, but this surface in this case has multiple things. So you basically have the top guy, which is going to be the paraboloid at 4. So you can imagine the paraboloid going like that. Then the sides of that part are going to be the cylinder. So you got a cylinder here. And then you got a bottom z equals 0. Okay. So you kind of have something that looks like that. Okay. Right. So you got this kind of like a cap and then like a soda can on the bottom. So remember that you had 3 different sides or 3 different surfaces, S1, S2, and S3. So in order for me to find the total flux, I gotta take 3 surface integrals in this case. So in class, we actually did the top guy because the top guy was actually the hardest one of all. So I'll set it up again for the top. So we knew that for S1, z was equal to 4 minus 3x squared minus 3y squared. So you can skip it. You can skip all of this part if you want. It's just me explaining this again. So we're going to parameterize this guy again. So this is a simple parameterization. So x equals x, y equals y, and z is just going to be this 4 minus 3x squared minus 3y squared. You can see that z is just going to be a function of x and y. So in order for me to find the flux, when we have a very basic parameterization, all we're just going to do is take the double integral over the region D, take the negative p g of x, negative q g of y, plus r dA. I'm doing a little bit of the shorthand notation for partial derivatives. So p, q, and r are going to be my force fields, and they're not really nice. Typically with these problems, they're nicer. This one's not as nice. Okay, but it could be worse. All right, so all we're gonna do now is plug everything in here. Now remember, because we are using a parameterization with x and y, we do not want any z's in there. We have 2 integrals, and those 2 integrals are gonna correspond with x and y's. So anything that has a z is gonna have to go away. So I'm gonna have my double integral. Negative p, okay, so negative p that has xy, okay, that's good. So negative xy, so we're all in the clear. And then the partial derivative with respect to x, that corresponds to this guy. Partial derivative with respect to x is just going to be negative 6x. Minus, now we have this q. My q component is going to be this negative 1/2 y squared. No z's there, so it's all good. Negative 1/2 y squared. Partial derivative with respect to y will be negative 6y. Plus, now r. R in that case is just z. Oh, but we cannot have a z in there because we're only looking at x's and y's. So z in this case is going to be whatever I parameterized it in terms of x and y, which is going to be this 4 minus 3x squared minus 3y squared. Okay? And this is just going to be dA. All right, over the region D. Okay, so I'm going to simplify this a little bit, and what I'm going to get is a double integral over D, 6xy minus 3y cubed minus 4 minus 3x squared minus 3y squared dA. Okay, and now what I'm going to do, well, I obviously don't want to integrate this guy. It'll be kind of hard because you have cylinders, so we need to convert it to polar. Okay, so you can see here immediately that my z values for my paraboloid are from 1 to 4. Okay, so we need to figure out what exactly is happening in that paraboloid when you're at z equals 1 and then at z equals 4. I need to know what's happening. So at z equals 1, I'm going to plug it into my paraboloid. So 1 equals 4 minus 3x squared minus 3y squared. You can see that this guy's just going to give me x squared plus y squared equals 1. So a circle of radius 1. And what's happening at z equals 4, and that should be kind of obvious if you just look at the picture. So you're going to get 4 equals 4 minus 3x squared minus 3y squared. And you'll see that when you solve for this, you're just going to get 0. So you got a circle of radius 0. So you can see that my radius in this particular part is going to be from 0 to 1. Okay, and we want every single side, so it's going to be from 0 to 2 pi. Now the horrible part is that now we need to plug in everything in polar form. So it's going to be 6r cosine theta, sine theta, that's going to be the first guy, minus 3r cubed sine cubed theta. Then we're going to get this should have been a plus 4. So fix that. So plus 4 minus 3r squared. And the reason why it's 3r squared is because you got this guy and this guy. If I factor out a negative 3, you're going to get that r squared. Now we're not done with that guy because now we have dA, which has an r dr d theta. Okay, and then I'm going to FOIL this guy out, 0 to 2 pi, 0 to 1. So foiling that guy, you get 6r cubed cosine theta sine theta minus 3r to the 4th sine cubed theta plus 4r minus 3r cubed dr d theta. Okay, now I'm not going to do the integration here because it is pretty crazy, but you can figure out that this guy's going to give you 5 pi over 2. I just don't want to make this video even longer than what it should be. Okay, so, but you can see that it's not, I mean, it's kind of terrible, but not too terrible. But here you would have to use some identities. So use substitution. This sine cubed, you would have to use some sort of like identity to be able to reduce it continuously. Okay, all right. So now what we got to do is we figured out the first one. This one we kind of did it in class. So S2 is going to be the sides of the cylinder. Okay, so S2 is the sides. Okay, which is the cylinder x squared plus y squared equals 1. And Z is between 0 and 1. So in order for me to work with the cylinder, remember with cylinders, you got to convert it to parameterize it. And doing so, you get it to cylindrical coordinates. So r cosine theta, in this case, r is 1. So you're going to get cosine theta. Y is sine theta. And Z is just equal to Z. Okay. And remember to find the flux with something that is parameterized a little differently. You got to take the double integral over the region D of F. And then I'm going to have to dot it with the cross product of both of the vectors. In this case, it's going to be theta and V, or theta and Z. Okay, so I'm going to have to do that. Okay, so let's go ahead and take the cross product. So luckily for us, we kind of already did this in the previous one, but I'm still going to do it anyways. So r theta, r sub theta, r sub Z. So I, J, K. So with respect to theta, the first one's going to be negative sine theta. The other one's going to be cosine theta, and then 0. And with respect to Z, is going to be 0, 0, and 1. And when you do this cross product, you're going to get cosine theta I hat plus sine theta J hat. And you can see that this guy is actually in the positive orientation. It's going outward. So this actually does make sense. So this is good. So now all we have to do is just plug everything in there. So double integral. My force field in this case, again, was that weird one. So the first one, oh gosh, what was it? It was xy. So xy, what I'm going to do is I'm going to multiply the x and the y here. Here's x and here's y. It's going to be cosine theta, sine theta. That's going to be for my force field, the first component. Then I'm going to plug it in for the next one is negative 1/2 y squared. It's going to be negative 1/2 sine squared theta. And then for my third component, I'm just going to have z, I think. Or what was it? What was the third component? It was just z. And in that case, well, I can't just plug in. Z is just going to be z. Okay, and I'm going to dot this with my vector that I just crossed, which is going to be cosine theta, sine theta, and then 0 over the region D. So what I'm going to end up getting is the double integral over D of cosine squared theta, sine theta, and then it's going to be negative 1/2 sine cubed theta, and then 0. I got nothing there. Okay, and now this is going to be dA. Okay, and now in this case, all we really got to do is just find the limits of integration. So the limits of integration in this case, well, if you think about it, you have this cylinder. So the cylinder, when we convert it to polar, would be from 0 to 1, because our cylinder only has radius 1, and it's all the way around 0 to 2 pi of cosine squared theta, sine theta, minus 1/2 r, oh, well, yeah, okay, cosine, sine cubed theta, all multiplied by r dr d theta. Oh gosh. All right, and then what you can see here is that you can just do this integration if you want. The r is not going to be as terrible because when you plug in the 1, you're just going to get 1. You're going to get the integral from 0 to 2 pi. Well, you're going to get 1/2, I think. Yeah, you're going to get 1/2 cosine squared theta, sine theta, minus 1/2 sine cubed theta d theta. Okay. Now you can do this integral on your own if you'd like. Here, this guy is just going to be a u sub. That one isn't that bad. The way that you would kind of do this one is that you might want to switch them into sine squared and then a sine theta. Okay, so break them up like that. Then if you remember from Calc 2, you can use this as 1 minus cosine squared theta, sine theta. Let u be the cosine, and then you can see that the du is going to come out from the sine. So doing a u substitution that way with an identity. And what you actually end up getting is a big fat 0. Okay, so a lot of things actually cancel out. And you have a whole bunch of signs. So that would be the total flux that's going across the cylinder. Okay, so that's kind of, so it's kind of telling you that the outward flux is kind of going in and out, and it's kind of canceling each other out. So the last one is S3. And S3 is just going to be, which one am I missing? I'm missing the bottom part, z equals 0. Now this one should be kind of easy, z equals 0, because in order to parameterize something like that, I can let x equal x, y equals y, and z equals 0. So my r of xy, my parametric equation, would just be x, y, and then 0. Notice that this is a very easy one, so a very basic parameterization. So in order to find the flux of this guy, let's find the flux, which is going to be the double integral of the negative pg. So negative p is going to be this negative xy. Okay, so I'm using the same formula that I did for this guy. So I'm using this same formula. So negative p. So it's going to be negative xy times the partial derivative with respect to x. So notice this guy is going to be my g of xy. So when I do that, well, isn't that just 0? So I'm going to get 0 there. My next one is negative 1/2 y squared. Partial derivative with respect to y is just also 0. And then plus r. R in this case is z. Okay? So we're just going to write z there. Okay? And this is going to be dA. Remember that z is not part of the parametric equation. Z is just equal to 0. So this guy actually goes to 0. So all we just have is a double integral over the region D of 0. That's just going to give me a big fat 0. So my overall flux is going to be the sum of all of these different sides, which is only going to account for one thing, which is 5 pi over 2. So my flux in this case is going to be equal to 5 pi over 2. Okay. So don't feel like it's always going to be like this, because sometimes you might have some flux in the other ones. But in this case, the only one that really took the hit was just this paraboloid part. Okay.